Section 3.1, the product and quotient rules. So remember that when we talked about addition and subtraction of functions when taking the derivative of sums and differences of functions, the derivative of sums and differences were then the difference in sums of those individual derivatives. But once again, I stated that that was not the case for the product rule. And so for the product rule, the derivative of the product of two functions, and so let's get this laid out right. If I take the derivative of some function times some other function, let's just call them f of x and g of x. So those are the two functions I'm going to take the derivative of, but they're being multiplied together. This derivative is then going to be the second function times the derivative of the first plus this first function times the derivative of the second. And so this is our formula for when we have a set of products. Take the second function, multiply it times the derivative of the first function, and then add that to the first function times the derivative of the second function. The quotient rule is a little more complicated, but if you can remember that layout that we have for the product rule, the quotient rule won't be so bad. So try to get the patterns right. So if we take the derivative of two functions being divided, that is the quotient, then that's actually going to be the denominator function times the derivative of the numerator minus the numerator function times the derivative of the denominator. And notice that that is a subtraction, and so the order in which you do this matters. And then that's all going to be divided by the denominator squared. And so those are our two formulas. That's how we take a product, the derivative of a product, and how we take the derivative of a quotient. So now let's see this in practice. So I have this y is equal to negative x cubed plus 2 in parentheses and x divided by 2 minus 1 in parentheses multiplied times it. One approach that definitely would work is you could multiply this all out and simplify it and then take the derivative of the individual terms. So using pre-cal simplification to then take the derivative of a polynomial. That's a perfectly feasible thing to do. It's all going to come down to preference. But we're doing product rule, so let's approach it as product rule. So let's define our first function and our second function. Well, the first function, f of x, that's going to be negative x cubed plus 2. Well, let's go ahead and take the derivative of that function, because we know we're going to have to at some point. And so f prime of x, or the derivative of that function, that's going to be negative 3. X to the 3 minus 1 is 2, plus the derivative of a constant is 0, and so negative 3x squared. Then what's our g of x? Well, our second function, g of x, is x divided by 2 minus 1. So then let's take the derivative of g prime. G prime of x is then going to be, well, the derivative of a constant times x is the constant, so that's 1/2. The derivative of a constant, that's the derivative of negative 1, is 0, so g prime is 1/2. Then, if we're trying to find y prime, we know that y prime, via our formula here, is actually going to be the second function times the derivative of the first function plus the first function times the derivative of the second. And so then, because I've done all this work already, we know that g of x is x over 2 minus 1 times f prime of x is negative 3x squared plus f of x is negative x cubed plus 2, and then g prime of x is 1/2. And then we could clean this all up, and that's going to be negative 3x cubed divided by 2 plus 3x squared minus x cubed over 2. 1/2 times 2 is 1. Then let's see if we can combine any like terms, and notice that we have negative 3x cubed over 2 minus x cubed over 2. Those will combine. I get that that is negative 4 halves x cubed, and then I have an x squared term, and then the constant, and then of course that will reduce to be negative 2 x cubed plus 3 x squared plus 1. And so we used our product rule to find our derivative. Notice here that we say find the rate of change of f of x at a point. Now specifically, at a point means we are going to be plugging in a value after we take the derivative. And so really we will be finding f prime of 1. But we have to take the derivative before we can plug the 1 in, so we need to do that. Now, once again, there are two good approaches here. The first thing you could do is if you wanted to take these two 4-term polynomials, multiply them out by the double distributive property, then you would get one large polynomial that you could then take the derivative of each individual term. That's perfectly fine. That would work. But because we're trying to practice the product rule, let's use the product rule. And so f prime is then going to be the second function. So that's going to be, notice I'm going to underline my two separate functions. Here they are. And so 2x to the fourth minus 10x cubed plus 15x plus 9 times the derivative of the first function. The derivative of the first function is then going to be 3x squared minus 5 times 2 times x to the first plus 2 times the derivative of x is 1 minus the derivative of 7 is 0. All added to, now we write the first function unchanged. That's going to be x cubed minus 5x squared plus 2x minus 7 times the derivative of the second function, which is then going to be 2 times 4x to the third minus 10 times 3 times x to the 3 minus 1 is 2, plus the derivative of 15 times x is 15, and then the derivative of 9 is 0. Now at this point, I'm going to try to clean it up as much as possible, and then I'm going to distribute this. And so I get that this is 2x to the fourth minus 10x cubed, nothing's changing here, plus 15x plus 9, and then 3x squared is 3x squared minus 10x plus 2 plus unchanged x cubed minus 5x squared plus 2x minus 7 times 2 times 4 is 8 x cubed minus 30 x squared plus 15. Now at this point, remember that what we're really trying to find is the rate of change, f prime of 1. And so honestly, why even try to simplify this further when really all I need to do is plug in that value 1 and then do the arithmetic to get the correct answer. So let's do exactly that. So f prime of 1, that's going to be 2 times 1 to the fourth minus 10 times 1 cubed plus 15 times 1 plus 9 times 3 times 1 squared minus 10 times 1 plus 2 plus 1 cubed minus 5 times 1 squared plus 2 times 1 minus 7 times 8 times 1 cubed minus 30 times 1 squared plus 15. Then all the arithmetic. I get that this is 2 minus 10 plus 15 plus 9 times 3 minus 10 plus 2 plus 1 minus 5 plus 2 minus 7 times 8 minus 30 plus 15. I then get that this is 16, so that's that piece, times negative 5 plus negative 9 times negative 7, which I then get to be negative 80 plus 63, or negative 17, as long as I don't have any typos. Now to find the derivative of a quotient. And so, once again, you do have to be careful, because remember that this is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. Alright, so that's our derivative. So then y prime is then equal to, and once again I'm just looking at my formula up here, the denominator, so it's going to be x squared plus x plus 7 times the derivative of the numerator. The derivative of the numerator is going to be 2x, the derivative of 1 is 0. Now minus the numerator, so that's going to be x squared plus 1 times the derivative of the denominator, that's going to be 2x to the first plus the derivative of x is 1, and the derivative of the constant 7 is 0. And so that's my new numerator for my derivative. Then over the denominator squared. So that's going to be x squared plus x plus 7, quantity squared. Then at this point, usually we'll just need to simplify the numerator. The denominator, leave it as is. If for some reason MyLabs gets angry, then simplify the denominator by multiplying things out. But for this one, let's just simplify the numerator. So I'm going to distribute that 2x. That's going to be 2x cubed plus 2x squared plus 14x. Be careful about this minus here. This minus is going to apply to everything. So I'm going to put a bracket here to keep myself safe. And I'll deal with that in a moment. So it's going to be minus this multiplication here. But I have a binomial times a binomial. So I could use the special case of the double distributive property, which is FOIL. And so that's going to be x squared times 2x, or 2x cubed. Outer is then 1 times x squared, or plus x squared. Then inner is 1 times 2x, or plus 2x. And then the last two, 1 times 1 is plus 1. All divided by this x squared plus x plus 7, quantity squared. Then to clean it up a little bit further, I need to distribute that negative sign, so that's then going to be 2x cubed plus 2x squared plus 14x minus 2x cubed minus x squared minus 2x minus 1, all divided by my trinomial squared, x squared plus x plus 7, quantity squared. Then clean it up further. 2x cubed minus 2x cubed, that gives me 0, so those go away. Then I have minus 2x squared, plus 2x squared minus x squared. That's then going to be x squared. So those are taken care of. And then 14 minus 2x, that's going to be positive 12x. And then those are taken care of, and then I have the constant term minus 1. Then I have the denominator x squared plus x plus 7, quantity squared. In some situations, simplification may be necessary, but I claim this is the derivative of our quotient. For this last example for 3.1, we want to do something similar to what we did in a previous section. And so we specifically want to find where is the slope of the tangent line of the function a certain thing. Specifically, the slope that we're considering is 5. Well, what's our game plan here? Our game plan is find the derivative of f of x. Remember that the derivative of f of x is actually going to be the slope formula for that function at any given point. But then, that's really slope, and since that's slope, we're going to then set it equal to 5, and then we're going to solve for x using methods that we know about. So, let's do exactly that. Step 1, find the derivative, and notice that we have a quotient rule. So, quotient rule says the denominator, 6 minus x, times the derivative of the numerator, that's going to be 0 plus 1, minus the numerator, so that's 4 plus x, times the derivative of the denominator, that's going to be 0 minus 1, all divided by the denominator squared. So, what do we then have? This is going to be 6 minus x minus, be careful with this again, that's then going to be this negative 1 distributed, which is then going to be negative 4 minus x, all divided by 6 minus x quantity squared. But be careful because now this negative gets distributed, and so then that's going to be 6 minus x plus 4 plus x divided by 6 minus x quantity squared minus x plus x, that's going to be 0. 6 plus 4, that's going to be 10. And so we're going to get that f prime of x is 10 divided by 6 minus x quantity squared. At this point, we now have to actually set up the equation we want to solve. So, set it equal to 5. Great. Then I have a rational expression. What are our tricks to solving rational expressions? Here we have a rational expression. 10 divided by 6 minus x quantity squared is equal to 5. And so I recall that when we're trying to solve rational expressions, if I have a rational equation, my fastest method is actually going to be multiply both sides by the LCD. And then I should have something that's easier to work with. And so that's what I want to do. My LCD here is 6 minus x quantity squared, 6 minus x quantity squared. Then what is that going to give us? Well, that's going to give us 6 minus x quantity squared divided by 6 minus x quantity squared is 1. So that's then 10 is equal to 5 times 6 minus x quantity squared. At this point, I'm going to FOIL this binomial, double distributive property, and so that's going to be 10 is equal to 5 times 6 times 6 is 36. 6 times negative x is negative 6x. And then inner is going to be negative 6x. And then the last terms is minus x times minus x, or positive x squared. And so then that gives me, coming down here, I get that this is 10 is equal to 5 times 36 is 180. Negative 6 minus 6x is going to be negative 12x. 5 times negative 12 is going to be negative 60x. And then 5 times x squared is plus 5x squared. At this point, we need to put everything on one side, and I'm going to do a rearrangement. Subtract 10 from both sides. And then that's going to give me 0 is equal to, I'm doing a rearrangement right now, 5x squared minus 60x plus 170. Then I have a quadratic. Now, I've played a few tricks with quadratics before, and I'm going to do it again. Now, I'm going to make my life easier because I notice that there is a greatest common factor between all three of these terms that I can factor out. And if I want to factor it out, because I have this 0 divided by that greatest common factor, as long as there's no variable there, will create a nicer trinomial that I can deal with. So let's factor it. If I factor, that's going to be 0 is equal to 5 times x squared minus 12x plus 34. And then I can divide both sides by 5. And 0 divided by 5 is 0. Well, then that gives me this. Then that gives me 0 is equal to x squared minus 12x plus 34. At this point, we could try to factor if we wanted, but I'll tell you that it doesn't factor nicely. And so then the quadratic formula is probably our best bet. And so quadratic formula, x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So remember, I'm just looking at the coefficients a, b, and c here. Then the arithmetic is going to give me 12 plus or minus the square root of 8, all divided by 2. Then we can simplify our radical. I'm going to use this little bit of space up here for some side work. So remember that the square root of 8 is 2 approaches. You can either do prime factorization, 8 divided by 2 is 4, 4 divided by 2 is 2, square root looking for 2 of a kind. There's 2 of a kind, it pulls out front. The other way to see this is the square root of 8 is really 2 times 4, which is then really the square root of 2 times the square root of 4, and the square root of 4 is 2, and so that's going to be 2 root 2, and so that's what we want. So this is then 12 plus or minus 2 root 2, all divided by 2, but then via reduction, that's going to give me 12 divided by 2 is 6, 2 divided by 2 is 1, 6 plus or minus root 2. And so I claim those two x values are the location in my original function where my slope is 5.